Alright, on the first set of problems, we are finding the domain algebraically and then supporting graphically. Let's talk about that for a second before we actually start. Anytime the directions state to do something one way and then support it another way, that means that the first way you do it is the way you should actually complete the problem. And in this textbook, you'll notice in your packet, and I've just started doing this with this packet, but the bubbles on the problems, you notice the little gray on the 10 and that 16 is gray. And if you turn the page and look, 18 and 20 then are not grayed out with a little gray circle on them. You'll notice the same thing in your book. Those gray bubbles mean don't touch a calculator. And that seems contradictory since it says support your answer graphically, but that just means you're using the technology as a support, but not as part of the solution process. So let's talk about domain. It would be good for you in general to start thinking of almost like if I have to list everything I bought from a store, then I can't possibly have bought something in a store that doesn't sell the thing I bought. So if we think about negative infinity to infinity, that's an interval that describes all real numbers. And when I say we can't do certain things or x can't be certain things, the understood ending to that, all those statements will be without making x something other than a real number. And for our purposes, the vast majority of what we will do will be with the real number set. So what you're going to do, as I state on page 2, so if at any point I keep referring to page 2 and you can't remember what I'm talking about, you might want to pause the video and look back. We're going to look for typically a square root or other even root of anything in an equation, or something like we have here on number 10 where we have an x in the denominator. And if you'll remember from Algebra 2, these are called rational functions because they look like fractions. And so the only restriction here, and this is the restriction on any denominator that contains x, is that whatever's there, and in this case that's x minus 3, cannot be 0 because you can't divide by 0. So we start analyzing for our domain by the fact that we write down what we know. X minus 3 cannot be 0. So we've just written this inequality in a way, not a non-equality, let's call it that. Alright, well then I can, even if I've put a slash through the equal signs, I can still use all the algebraic properties to isolate x. So I add 3 to both sides. So I know that x cannot be 3. Well, that's saying what x can't be, but stating the domain is listing all the values of x that x can be. So I start with negative infinity to infinity as my starting place. So you always work from left to right for the domain, as I mentioned on page 2. So, and we always use parentheses with the infinities, but then when we list our number, the symbol we put depends on whether or not we want to include it. Well, obviously here we're excluding 3, so that means that 3 is not part of the set. It's up to 3, but not including it. So the first piece of our domain is negative infinity to 3, union, 3, that was supposed to be a 3, try again, 3 to infinity. And then you put a big capital D in the front of it, and that's the proper notation for stating your domain. And the reason you know that's it is that there was nothing else in the equation that was a problem for x. Alright, so then the direction is stating that we're going to confirm graphically. Now I want you to notice something before we look at the graph. Notice that you have a piece here and a piece here. Anytime you have that as your domain, you should see that in the graph when you graph it. So let's look at our graph, and here it is. So here are the pieces that I was referring to. I have one piece here and a second piece here, and these are the pieces that correspond to the domain that we just wrote. And so this piece corresponds to from negative infinity to 3, but not including it, and this piece corresponds to 3 to infinity. And another little side note here is that when anytime you graph on paper, any dashed thing that you draw is not considered part of the actual graph. Only the parts which I've highlighted here, the red solid lines, are actually part of the graph. So let's move on to number 14. Same directions, find algebraically or analytically, and then support your answer with a graph. Well, now this one's obviously got more going on than the one in number 10 did. But even though the denominators are the same, we're going to reenact it because I want you to see the process you should go through for a rational function with multiple restrictions. You should always check the top. Well, if you look back at number 10, the numerator was 5. There was no x there. If it's a number, there's no way it can put a restriction on x. X can only be restricted where you find x. So when you have a rational function, you should start with the top every time. So we're going to look at the numerator first. If you don't get in the habit of doing that, you're going to wind up focusing on the denominator just because it tends to be the most frequent issue, and then you're going to miss a chunk of credit or maybe complete credit on a homework or test question because you didn't check the numerator first, because you'll forget to do it. But in this case, the reason there's a restriction in the numerator is the fact that we have the square root there. And remember, that was your other red flag I mentioned on page 2. So I'm just going to put the square root symbol. So when you see a square root, then you should take whatever is inside it, and in this case that's 4 minus x squared, and write what you know about that statement. What has to be true for a square root? It has to be greater than or equal to 0. So then again, algebraically, you isolate the x, and so in this case the easiest way to do that is to add the x squared term to both sides. And I don't know why I put a 0 there. So when I add x squared to both sides, I get 4 is greater than or equal to x squared. I'm going to show you the analytical way to do this, and then I'm going to come back and explain to you how you can complete this problem without what I'm about to show you. In the same way that when we solve absolute value equations, because of the two possibilities involved, we have two different statements. When there's a square term involved, then you can copy the, and let me try this again. If I were to take the square root of both sides, I would get 2 is greater than or equal to x, and then I would get, and notice that I put the 2 where the 4 was, the x where the x was. Well, then when I write the other one, then I can write negative 2, and when I write the negative, I reverse the inequality, and then that's x. So this tells me that x has to be, this one says x has to be bigger than negative 2, this one says x has to be smaller than negative 2. So for the domain of my numerator then, and it can equal either 2 or negative 2, I'm going to have negative 2 to 2. Now I promised I'd tell you another way to do that, so let me do that real quick. If you look at this statement, you got to think, what kind of number can I square and have a result that's going to be smaller than 4? Well, if I square a number bigger than 4, like 5, that's clearly not smaller. If I square a number that's bigger than the square root of 2, say 3, I'm sorry, the square root of 4, which would be 2, then like if I square 3, it's too big. But look what happens if I square a number that's between our two numbers we found analytically. What if I square 1? That's definitely smaller than 4 because 1 squared is 1. If I square 0, that's smaller because 0 is smaller than 4. So those are your options for ways to think about it. But so far we already know we've taken our starting interval of negative infinity to infinity. That's the one that should be in the back of your mind every time you do a domain. Well, we've already narrowed it all the way down to this little negative 2 to 2 range. Or not, don't say range because that sounds like we're talking about something else, but that interval. So then let's look at the denominator. And this one's going to go much faster because it's much simpler. So remember, when you have a denominator with an x in it, just write the statement that has to be true, because denominators cannot be 0 because you can't divide by 0. So you write the factor cannot be 0. So then you isolate x in that statement. And if I add 3 to both sides, I get that x cannot be 3. Well, if you look at your original And this is what you have to do. Once you've done the numerator and the denominator separately, you have to take this value and go back up to your numerator domain. Because that's basically what your working domain is when you move on down to the denominator. But 3 is not in between negative 2 and 2. It would be outside it, so it doesn't get involved. So it becomes irrelevant to our final answer, which is that the domain, let's try that again, our domain is negative 2 to 2, including my endpoints, and I show that with the brackets. Now we're going to confirm graphically. And this is a strange little graph, and you need to pay close attention in this one to appreciating just how small it is. And if you need to graph it, you want to pause the video and graph it in a standard viewing window on your calculator. You'll see what I'm talking about. But notice here that my smallest x value in this picture is negative 3. My biggest x value is 5. And negative 3 is way down here. And look where the 1 is on the y-axis, way up there. So I'm counting by a scale of 0.2. So this is actually negative 2, and this is actually at positive 2. So there's my interval notation showing up in my picture. Just like in the first one, I had a two-piece domain, two-piece graph. In this problem, I have a one-piece domain, and it's a small little domain, so I have a small little graph, one piece. So there's a definite correlation between an analytic approach to finding domain and the graphical approach. On to number 16. Here it says to find the domain of the function algebraically, support the answer graphically one more time. And so when you look at this one, because you see those even powers of x that we can factor out, your first thought should probably be to do that. So let's pull out an x squared, and we get x squared minus 16, still all under the radical. But then I can take the square root of those pieces separately and get this result. Now, because of the way this function is set up, I'll tell you what, let me hold that thought till we go back and look at the graph after we're done. Alright, well obviously the square root of x squared is x, or some variation of it, but I'll tell you what, let's go ahead, this is what I was about to say. When you start with an x squared, your output is always going to be positive, so we have to restrict x to be positive here, because otherwise we're writing a different function. And if that went over your head, that's okay, just let it fly on by. It won't impact our answer. Alright, and then we go to the remaining square root, and we can't do anything with it in its current state, so we'll keep it. Alright, so we've kind of rewritten the function to help us think about it here. Alright, this one is going to be a little bit weird, so bear with me. And so you might even want to put like a star beside this one in your notes as a reminder that this one's kind of an upper level example. But as I promised you at the beginning of the course, I'm not one of those teachers that's only going to show you the simple, straightforward ones. This one's a little tricky. Alright, so let's do this kind of the simple way first. Let's hold off on the fact that that x is sitting outside, and let's focus on this other piece over here that has the square root remaining on it, because we know that whatever's inside there, which happens to be x squared minus 16, has to be greater than or equal to 0. And then if I do that, then I can add the x squared to both sides after I've written that. So I know x squared must be greater than 16. Well, what do you square and get a number greater than or equal to 16? You square 4. So you basically, it's like you're taking the square root in your head when you look at this, or you can just kind of make yourself a note that's what you're doing. And the positive possibility is that, oh wait, I just screwed that up, sorry. Try that again, let me rewind. Okay, if I take the square root of both sides of this, I would be left with x is greater than or equal to 4. But it's technically plus or minus 4, but you can't write it when it's an inequality. So as I mentioned on the last example, then when you consider the negative possibility, you have to reverse your inequality. So x is either greater than 4 or less than or equal to negative 4. But do notice that that includes the equal, which means we're going to include our 4's. Alright, so based on this, my domain would be negative infinity, because I always start at negative infinity. And we're talking about this piece over here now. Try that again so it doesn't look terrible. It's better. All right, so this is the one that's working from the left. So we're going to start from negative infinity, go to negative 4, and include it. And then we're going to have, and I'm going to leave a space and come back. That's going to be where I'm going to put my answer to the what we do about the x on the outside. All right, and then for x greater than or equal to negative 4, we're going to, I'm sorry, to positive 4, we're going to put 4 to infinity. So we've got that, all right? But now let's come back to this x. If you come back to your original function, x to the 4th minus 16x squared inside the square root, and now we've done the analysis to figure out what numbers work in general. You always need to come back and look at x, especially when we did the analysis over here to determine that we were going to wind up with that x on the outside of the square root. 0 works here because 0 minus 0 is still 0. So we should have union 0 union that interval. So basically there's technically a 3-piece graph involved in this, but let me show you what your calculator is going to tell you, because this is another one of those moments where your calculator tells you a little bit of a fib. When you graph this on your calculator, you are going to see what's here, give or take exactly how yours shows the same graph. And you can see that I zoomed way out because my upper limit here is 107 and my lower limit is negative 40.5-ish. So clearly this is not the standard viewing window. So what you would see if you're in standard mode is going to be a little bit different from this picture. All right, but notice that it is 2 pieces. We are at 4 and negative 4, and we do know that these are closed dots because we figured out that it could be equal to 4 and all the algebra is still legal. All right, but what this picture doesn't tell you, and it never will, it will never include a stray point like we're going to have in this graph. There is a point at the origin because when I plug in 0, I get 0. And let me show you what I'm saying here. F of 0 equals the square root of 0 to the 4th minus 16 times 0 squared. Well, obviously, that's the square root of 0 minus 0, which is 0. So now I know that the point 0, 0 is part of this function, but your calculator doesn't show that. So just be mindful of that. So this doesn't violate my rule. I told you that you're going to have the same number of pieces in your graph that you have in your domain. So this piece over here is our negative infinity to negative 4 bracket, and that's why the dot is closed. And your calculator also won't show you whether the endpoint of a graph is closed or open. More on that later. All right, and then here's our 0 that we included in our domain. And then over here we have our piece of the graph that corresponds to the 4 to infinity part of our domain. So then we just put that's just proper notation to put those U's for union, and that's what that stands for. So if you're good with me up till this one, you're still in pretty good shape, so don't panic. Let's look at the last couple on this video, because now we want to talk about range, and this actually becomes a much simpler conversation because of the fact that for the purposes of our course, until you know functions really well, I will never ask you about their range without your graph or a graphing calculator. And in this case, I went ahead and graphed them and put them in your packets for you, but when you're doing the homework, you'll graph them on your calculator and use your calculator to determine whether or not all the points are included. Since, for instance, in this picture, and I'll put a little rough sketch of the shape of the curve while you're looking at it on your paper, but it's going to look something like that, kind of free floating out in space. And I actually showed the grid lines on my graph before I put that in this document, but the grid lines aren't showing up very well in the copies. So you can use the scale on the x and y axes to count over to figure out that the coordinates of this point where everything starts or stops depending on your perspective is the point 4,5. So we have to figure out what's happening at this point because your calculator just tells you that's where the graph either starts or stops, again, depending on your perspective on the graph. So there is clearly a point here, but now we've got to decide whether when we emphasize that point, it's closed or open. And I'm going to show you a couple of ways to think about that. Way one is to plug that x value into the function and see if anything bad happens. So I'm going to plug in 4, and I'm going to get 5 plus the square root of 4 minus 4. Well, something dramatic is going to happen, but this is not bad because it's legal. That gives me 5 plus the square root of 0, which is just 5 plus 0, which is 5. So when I say bad versus good, good means everything's good, means that we got an output that works from our input that we used. So that means that I know this point in this graph is closed. Well, what does that have to do with anything? Well, as I told you on page 2, when you are describing a function, or a function's range, which is what we're doing here, and again, we're going to put our answer with a big R like we put the big D on our domains. So again, we start from the smallest possible y value, which would be at negative infinity. Well, this graph doesn't go to negative infinity, so we're going to start at its smallest value, which is 4. So we're going to put a bracket because we just proved analytically that it could be 4. And then it's going to go to infinity. So if we were graphing this on paper, you would have an arrow out at this end. And so this is the range of this function. Now I want you to notice that the range has to do with the y-coordinate. As I had on the front of your sheet, or the front of your packet, domain x rangey, that's what's going to keep your thinking straight. And that's why we start at the bottom and go up. And we all intervals should, this should be the smallest and this should be the biggest every time. And I'll probably start taking off a little credit eventually when you don't do that. All right, on to the next one. Again, got a little uglier one to work with here to close out this section. Again, we're finding the range, and just like I said with the domain where you're starting from negative infinity to infinity, that's kind of where you want to start every time you're doing domain or range. The reason we didn't on that last one was it was clearly a more shortened version of the range, given that there was only one little weird blip out in the middle of the picture, relative to the way typical graphs look. All right, so let's look at this graph. If I start from the bottom and go up, even though it's on both sides, that doesn't matter, because what you're thinking about is what are my y-coordinates. As I move up this graph on those bottom pieces that you see on the paper, either way, at whatever level I'm at, these y's would all be the same. If I draw a horizontal line across, I'm going to have the same y from there. So we start from the bottom. So you just focus on either piece when they're reflected pieces like that of the graph. So our range is going to start with negative infinity because it goes off the bottom of the picture. And we'll talk more later about how you'll know what happens outside that window. So we're going to start at negative infinity, and then when we go up, something weird happens before we get to the x-axis, and this thing shoots off into the far left and the far right. Well, if you look back in your packet or if you read through the section as I would hope you would have, you remember that we talked about horizontal asymptotes occurring like this. And if you look at this one, where your graph at the bottom, okay, here's the x-axis, and then at the bottom you see these two pieces that look something like this. Well, the line that's steering those two pieces is parallel to the x-axis but below it at 1. And the way you would know that is based on the fact that we have a horizontal asymptote there. That relates to how we find horizontal asymptotes, and we'll talk about that in later examples. So, but you can see if you just take your ruler and draw a straight line across at where the y-axis shows 1, and just go straight across, that's where the graph is being steered. So that tells me when I come up from negative infinity, I'm stopping at negative 1. So I put negative 1, and I put a parenthesis, because this thing will never equal negative 1. It's going to keep trying to get there, and that's why it gets closer and closer and closer, but never gets there. All right, and then from there, as I'm moving up vertically, the next thing I'm going to run into, as far as the graph goes, is that U-shaped piece at the top, or the sort of parabolic piece at the top. So I need to figure out what my y-coordinate is at that dip in that U-shaped piece. So to do that, I look at my